This is Viterbi Voices, your chance to hear stories about research, classes, student life, and more.
Directly from our students, faculty, and other members of our engineering community. All right here at the USC Viterbi School of Engineering.
Welcome back into Viterbi Voices. This is another bonus episode, another department faculty roundtable session. My name is Paul Ledesma. I'm the Director of Undergraduate Admission here at the USC Viterbi School of Engineering. Again, as an intro, it's just me on this one. Audrey is still in Denver, still doing well as she wraps up her junior year taking classes remotely. And I'm here in my home. I'm in Redondo Beach, California. It's been raining all week, and I really just want the sunshine to come out because I would like to sit outside for a little while, and I would like it to not be 50 degrees, which is weird for April. Anyway, this episode, another bonus episode, another department faculty roundtable session. This one is all about astronautical engineering. So we've had a few other episodes so far. We're just going to be cranking these out and getting them up as quickly as we can and not holding to our regular podcast schedule. With astronautical engineering, we have three fantastic faculty members that join me for the conversation. The chair of the department, Dr. Dan Erwin, professor that teaches the capstone course, Professor Dave Barnhart, and also Professor Garrett Reisman, who is a former astronaut spending over 100 days in space and also working at SpaceX and teaching a lot of really great courses on human space travel. There's so much to dive into in this conversation. I can't even give you a summary of it, but it's all about astronautical engineering, and we talk a lot about the differences between mechanical and aerospace and astronautical engineering and how that all kind of winds together in the curriculum. So when you're looking at these disciplines, you can understand those differences. And if you want to learn a little bit more about aerospace and mechanical engineering, I point you to the previous episode where we had our faculty in aerospace and mechanical engineering. At the end of the day, I think the key here is that there is no right answer. They all are great degree programs. No one under-prepares you or over-prepares you for a specific profession. Nothing pigeonholes you. It's just all about your interest and what you think sounds interesting to spend time working on. So enjoy this conversation with astronautical engineering faculty, and hopefully we'll see you on the next episode. All right? Have a great day, and I hope you're all staying safe. Hello, everyone, and welcome to the Department Faculty Roundtable for the Astronautical Engineering Department here at the USC Viterbi School of Engineering. My name is Paul Ledesma. I'm the Director of Undergraduate Admission at the USC Viterbi School. It's a pleasure to have you all here. Today, all about astronautical engineering, and we've got three fantastic faculty members to talk to you about astronautical engineering. I'm going to let each of them introduce themselves. We'll start out with the chair, Dr. Dan Erwin.
Hi, I'm Dan Erwin. I'm chair of astronautical engineering. I've been with the department for some years. In fact, I was one of the people who founded it in 2004. Before that, I was a faculty member in aerospace engineering, so I know that program also pretty well. And I've worked at a couple of aerospace companies, Lockheed and Aerospace Corporation, but mostly I've spent my life in academia.
Great. Thank you, Dan. Let's move on to Dr. David Barnhart.
Hey, everybody. It's Professor David Barnhart. Appreciate it. I actually came from industry and government, working there for many years. Right now, I'm a research faculty member in the Department of Astronautical Engineering, and also director of the Space Engineering Research Center that is affiliated specifically with the Astronautics Engineering Department. We can talk about here very shortly. So thanks much. Pleasure to be here.
Absolutely. And Dr. Garrett Reisman.
Hi, everybody. Let's see. I am the new guy. I've only been in the department or at USC for just under 2 years. At the end of the semester, it'll be my 2-year mark. And prior to joining the faculty here in astronautical engineering, I was working in industry. I was at SpaceX, and I did a bunch of different jobs at SpaceX. My most recent position was Director of Space Operations there. And prior to that, I was at NASA, and I was a NASA astronaut. So I flew a couple missions up to space, one in 2008 aboard Space Shuttle Endeavour. And on that mission, I spent 3 months aboard the International Space Station. And then my second mission was in 2010 aboard Atlantis, and there we spent just under 2 weeks aboard the space station again. Came back home on Atlantis. So had that experience at NASA. Before that, I was at TRW as a guidance navigation control engineer, and before that, I was at Caltech doing my PhD in multi-phase fluid mechanics a long time ago. So and now I'm here at USC.
All right. Well, great. As you can tell, a lot of fantastic backgrounds here and lots of things to talk about. For our guests that are joining us, you should know what we're going to do is we're going to talk about the department in general. I'm going to lead them through some questions to discuss, and then get your questions ready. We'll have an opportunity toward the end to take questions from the audience. No questions right now, please. But when I open it up for questions, I'll have you go to the chat window and have you layer them out there, and we'll get to as many questions as possible. I think to get us started, as a whole, why don't we start with what the heck is astronautical engineering, and how does it differ from something like aerospace and mechanical engineering? And we have a number of our guests that were in the aerospace and mechanical engineering roundtable from yesterday. So whoever would like to take that, or kind of you guys can argue amongst yourselves about it.
Well, I can sort of I'll start with how it is from the academic point of view, and you guys who have actually been there on the front lines can override me, especially if I say something wrong. But here's the thing: there's a bunch of different engineering majors, and they all kind of think differently, and they all have a different approach to everything. Aero, astro, and mechanical are in a way all the same thing, because we sort of see the world from a mechanical point of view. Aero you can think of as being mechanical with an emphasis on flying vehicles. Astro you can think of as being mechanical with an emphasis on space vehicles. So our stuff goes in orbit in space, or it flies through the atmosphere. For us, the atmosphere is just kind of a disturbance. We would rather it weren't there. And so many of the underpinnings of all three majors are really, it's the same for all three. And in fact, academically, when you take courses, a lot of the courses that you take are the same: statics, dynamics, strength of materials. But you specialize in courses in orbits, rocket propulsion, spacecraft communications, space environment. There's a bunch of things that are kind of unusual. They only happen in space. And of course, from an engineering point of view, one of the things about it is that that spacecraft, once they're in orbit, unless you go up there on the space shuttle, which we don't have anymore, you mostly can't actually work on them. You can do software updates if it's a well-designed spacecraft, but you can't actually physically work on them. So it's incredibly important that the spacecraft be very reliable, that it not have what we call single point or single string failures. In other words, something where one thing, if it fails, will bring down the entire mission. So one thing that we say about spacecraft is that a spacecraft is an tightly coupled complex autonomous system that operates in an adverse, in other words, a hostile environment. Now you can make the same argument about an iPhone in a teenage girl's back pocket. And a lot of stuff that's on the iPhone and a lot of the design considerations actually are not that different from a spacecraft. But iPhones get replaced every year or two, and spacecraft don't. They stay in orbit without being touched for years. So there's actually quite a bit of difference there in terms of reliability.
But actually, speaking of that, one of the things that the astronautics department specifically is doing, and it's a huge passion of my own, and the cool thing is that I've been pushing to try to get into making the change in space specifically to go up and repair spacecraft so that we can go up and finally do things to satellites that otherwise you couldn't touch after you get up there. And the cool thing is that Garrett's actually been up there. He's actually seen many of the things from an interoperability standpoint. So a lot of the things that we're beginning to work on from a research standpoint that I'm lucky enough to bring into the department is this concept to think differently about how a spacecraft is defined. Instead of arguably, yes, there is mechanical structures, but really the heart and soul of spacecraft or satellites ends up being a whole bunch of electrons and bits that are flowing around, communicating with cameras and things. And so we are doing quite a bit of work specifically on how do you update that? How do you modify that? And most especially, the cool thing is today's environment, literally over the last year, was the very first sort of servicing mission in space. Northrop Grumman was the one who just put it up there. One could argue that servicing has been going on for the last 25, 30 years, specifically with manned presence in space. And that's sort of the really cool things. We're now beginning to reach out to create robotic systems or autonomous systems to go up and correct, refuel, reconfigure, reconstruct, repair satellites. And that's one of the things that we're actually working on here in the Department of Astronautics.
Yeah, I think those observations are really spot on with regard to what's happening in space flight, or robotic space flight. And the other thing I'll add to that is the other thing that's happening that's revolutionizing the industry is the cost of access to space is coming down dramatically just over the past couple of decades, and or just past decade, I should say, and that's opening up new possibilities, new ways of looking at it. So in the past, we had to make these massive billion-dollar satellites that were going up to geo orbits, and they had to last forever. But now we're looking at constellations of thousands of small satellites flying around in lower orbits, where they're not disposable. They're still expensive. These things are still not cheap, but it's getting to the point where you can tolerate a couple of them breaking, and then just have it with the low cost of access to space. You can launch new ones and replace them. So it is a bit of a shift, and it's interesting to see how the industry is moving. But my particular interest is actually not on the robotic side; it's on the human side. And so the courses I'm teaching in our department all have to do with human spaceflight. And there, as Dan was explaining before, the requirements for redundancy, for reliability, for safety are still extremely, extremely high. You can't make a space station that you're going to put people on that you can tolerate failures and just put up a new one when it breaks. So on that side of the house and that area where I've been focusing my efforts, is still, reliability and safety are still paramount.
That's really helpful. Thank you. Dan, would you mind maybe giving an overview to our guests? Obviously, they've all been admitted to the school. A good number of them admitted directly to astronautical engineering. Some of them are thinking about it. What can students expect from the undergraduate curriculum in astronautical engineering? I know you started touching on some of the courses and how it overlaps with aerospace mechanical, but can you give kind of a 30,000-foot view of what those courses are going to be like, and then specifically what students can expect from the introductory course?
Yeah, sure. Well, okay, to begin with, we're a smaller major. There aren't that many faculty, and it's a smaller student body in our major than it is in either aerospace or mechanical or electrical or chemical for that matter. Actually, chemical, I'm not sure, but so we're a small enough major that we know pretty much all of our students. And actually, this fall, I'm going to be teaching the introductory course, Astro 101, where you, on the first day, you come in and it's like your first introduction to what engineering in college is going to be like. And all the majors have 101 or 105 kinds of courses which introduce you to the major. And the idea is to sort of, it's more kind of motivational and to get your feet wet and try to orient you in terms of what engineering is and of course what the field is. And by the way, I'll mention, since we have a big group, I'll tell you that it's very important that if you're here as an engineering applicant, that you be there because you want to, not because somebody else told you engineering was a good major or a good thing to do as a career. Because the thing about engineering is you get to work on stuff and how things work and design and all kinds of things. And for the right kind of people, if you have the right personality, you love it. It's better than anything. But if you're not that kind of person, then you'll hate it. Engineering's really bad if you're not supposed to be an engineer. And I'm not talking about being smart. You guys are all smart enough. I mean, whether you're that kind of person who enjoys it. So be there because you want to. So one of the important things about any of the 101 courses in any major you take is that when you come out of it, you should be more enthusiastic than when you went in. You should be saying, oh yeah, I want more of that. And actually the 101 courses, they're not that rigorous. You haven't had that much math and physics yet. So the kind of heavy hitting stuff that you get, and there is a lot of hard things in an engineering major, but in the 101 course, it's really more introductory. It's kind of a survey. You may have speakers come in and describe their work. When I teach it, I like to have examples from other fields of engineering too, and just to show what the whole thing is like. And one of the things about engineering is any system that you make, whether it's a car or a spacecraft or an airplane, it all has almost all fields of engineering in it. Every piece of engineered equipment now has, 1 to 10 million lines of code in it. A car has 7 microprocessors in the front bumper. I mean, so I did mention that we view things from a mechanical engineering point of view, but all of engineering is much more interconnected than that. So whether it's astronautical, whether it's biomedical, anything you go into, you're going to be seeing all aspects of engineering. Now, in your freshman year, the most things that you take are math, physics, chemistry, that is general courses, and of course general education, writing, and you tend to get more into your major courses in the sophomore and junior years, when you take the kind of the core underpinnings of the major that are typically built on top of calculus and physics and differential equations. And those are courses in aero, astro, and mechanical. Those are courses mentioned in statics, dynamics, strength of materials, and also computational things, computer-aided design, modeling and simulation of systems. And in the sophomore year is when you get you start to get a series, you're first in a series of the core astronautics courses. And that is Astro 280, which is taken by both Aeros and Astros. And in that course, you get your first serious introduction to orbits and rockets and attitude dynamics and space environment. And then in your junior year, there's a 2-semester course in spacecraft systems, which starts out by looking at all the different things that a spacecraft has to do, and things like communication, attitude dynamics, and control, orbit control, launch vehicle integration, and then that goes on to teach you about design, because design of any complex system, including spacecraft, is a heavily coupled thing where you can't just you can't have one person working on one part, never talking to anybody else, because everything you do on a spacecraft affects everything else. And so it's a kind of a highly collaborative process where you have to make trade-offs, because among other things, for spacecraft, mass is heavily limited, volume is heavily limited, and if one subsystem decides that it needs to have a bigger, heavier thing, everybody else is going to push back against that. And if somebody needs more power, that impacts the power system, and there may be less mass for the power system, which isn't going to work. There's all kinds of trade-offs and design decisions that have to be made, and you get your first introduction to that in your junior year. And then starting in your junior year, you'll be taking also technical electives, which are not specific required courses, but courses that are supposed to be in general technical areas, but you get to pick what they are. And you can specialize in astronautics courses, because we have a lot of specialized courses, primarily at the master's level, because it's fortunate that we are in the space industry. The city that is the hub of the space industry. And so there are all these space corporations around, and all these people that have been in the industry for decades and know all the ins and outs of how to build spacecraft and what can go wrong with them. And they actually instruct in our master's program. And you can take those courses, those specialized spacecraft courses, while you're still an undergraduate. Or you can branch out and take technical courses in science, in astronomy, for example, or physics or chemistry, or another area of engineering. So technical electives are an important feature of our program. And then in your senior year, you take a couple I'm sorry, I forgot it. Also in the junior year, you take a substantial 2-semester laboratory course where you learn how to do things in the real world, how to record things on computers, how electronics interface with the real world. Because inside a computer or a piece of electronics, everything's a voltage or a current or digital bits. But outside in the world, these are mechanical effects. A sound signal, for example, is pressure and air. So you look at how one thing is converted to the other. A microphone, for example, is a vibrating object which creates an oscillating current in a surrounding coil, is one way a microphone works. So there's a bunch of things you learn in that lab course, and you come out the other side able to actually build and use electronics and do things that control the real world with motors, and be able to record things that are happening from the real world. And then in your senior year, you build on that by doing a senior project lab, which is a thing done in teams. and you do a capstone design project. This is true of all engineering majors. In our engineering major, that is the capstone course, which is taught by Dave Barnhart, by the way, is a mission design course where you kind of pull in everything you've learned over your 4 years. And again, in a team, you work out a design for an entire space mission, not just the spacecraft, but everything about the mission, because of course, a space mission is much more than just one spacecraft.
I would say if anybody else had anything more to add, but I think that was an encyclopedic production of the curriculum.
Well, professors can talk. That's what we do for a living.
Exactly, exactly. But Professor Barnhart, that mission course, that might be interesting to learn a little bit more about our students, where this all leads as far as capstone.
Most disciplines typically have a final either design or project type course. So the ASTE 421 is that course inside the astronautics department. And as Dan indicated, it's we treat it almost like it's depending upon each year we come up with an interview, or what we do is we give a request for proposal. So something that's very similar to what you might see when you get into industry in terms of a customer offering an opportunity, and then you as an engineering team, because it is a project course and it's a team course, have to come up with the best design or the best mission, and then sort of defend that at the end of the semester relative to what we've come up with. So each year it's different. This year, as an example, because of the great interest to return to the moon, we've actually given a challenge to the two teams to come up with the best business plan that supports communications, transportation, and navigation around and on the moon. So they're actually coming up with that. Traditionally, what we also do is at the end of the semester, the class itself, broken into teams, have to give a large presentation as well as write a report about how they've described both the technical and the mission aspects of whatever it is that we put together. But then what we also do is we invite in, as Dan said, we have a very rich and robust sort of expertise in the area. We invite in experts from all around the Southland and Los Angeles to literally sit, and these are practicing engineers that are out in almost every industry that we can try to pull in to evaluate what the students have done, what the team has done. They provide really good questions, putting everybody on the spot, which is almost exactly the way it is in real life. And then they also provide recommendations about things to think about or consider. So it really is, the other thing about the course is we don't teach as much as we offer an outline and things that we want them to do, and then guidance along the way. But the whole point is they have to go all the way back through those past 3.5 years and gather all the stuff that they've done to try to put it into practice.
I think that segues nicely to another topic. You know, we talk a lot about the school in general having a collaborative approach to education and teamwork being a priority. Can any of you talk about the importance of teamwork in engineering problem solving, and even how that applies into industry as we move on?
Well, from the industry perspective, I could tell you that, you know, you're going to go off, if you go off to work in aerospace and being a member of a team, it's very rare that you have one person as purely an individual contributor that doesn't interface with anybody and just does the work and submits the results. Some very specialized areas perhaps, but for the most part, working as a member of a team is going to be essential. And really, what I found at SpaceX is we had some people who were incredibly intelligent and had a lot to offer technically, but were terrible at working with others. And as a result, they were not very helpful to have at SpaceX, and a lot of them, you know, didn't last very long. So I think it is essential along the way as part of your engineering education that you learn how to work collaboratively. That's super important for everything you do after you leave your undergraduate experience. And so one of the things, for example, I do in my courses, a lot of us do, is we have, you just heard David talk about the group projects that you do as part of your capstone project. But that goes on to in other classes as well. So I have a lot of group projects in the courses I offer, where we have groups working on basically the same problem with the same test setup, but get widely different results and have to work together. And what I found is the groups that get the highest marks are the ones that work together most well as a team, not necessarily the ones that are the smartest or even the best. So that element of the human interaction is really important.
Thank you. Anything else you all want to add? I don't know if I cut anybody off. I'm sorry. Okay. Why don't we talk a little bit about research? What does research mean in the Astronautical Engineering Department? What type of research is going on? Maybe some specific projects you're all working on or things you're excited about in the industry moving forward. It's a broad question, but whoever would like to pick it up.
So Dan and Garrett, if it's okay, and if we can share the screen really quickly, then I can sort of walk through at least one element of the kinds of research that we do.
Oh, you're a co-host.
Okay, got it.
You can share your screen.
Let's see if this works. Does that work? Awesome. Okay.
Yeah,
Well, so relative to the astronautics department, there are a number of research activities that each of the professors are working into. Both Garrett and Dan will have some to talk about. I'll take this opportunity to just give you a sort of a broad brush of this thing that we've called and created called the Space Engineering Research Center. In essence, it's a joint collaborative activity with the on-campus Department of Astronautical Engineering, which you guys have all participated in. Congratulations and appreciate you're here. And an off-campus research institute called the Information Sciences Institute. So I'm lucky enough to have some modest laboratories to be able to do some cool things that are specifically located in, are dedicated to space. What I'll try to do is, let's see, I have to get to, oh, I thought I could do the page down. Anyway, what I can talk to you about is the kinds of things that we do. Just to give you a quick update, we are the group, the center that has actually done the first spacecraft that have been put into orbit. They are CubeSats or nanosatellites to date. The first one was put up was Keras. The second one was this one called Aeneas, and we had a really unique aperture that went up. The third one, which is actually in the clean room, it's called the Donna. And then I have another one, which is a class project that was done this past year. So we actually are able to do full spacecraft design, development, integration, and test. We have a modest clean room, a class 100,000 clean room that's out at the Space Engineering Research Center at ISI. There you see a picture on the left-hand side of, you're actually looking from the clean room outside. So we have a collaborative environment that allows for clean activities to occur, and then a tent structure so we can actually project real-time communications to test things that are up there. The other kinds of things that we're working on is looking at swarms of spacecraft that are flying together. Garrett talked about sort of the new activity is constellations of small satellites. You can take that to the next step where you have satellites that are interacting with each other in close proximity. That in and of itself is a rather strange and new and really exciting, robust research area that is out there we're trying to get into. On the right-hand side of this picture, we also have, we're lucky enough to have, we got investment both from the Astronautics Department as well as the Dean, a fully operational satellite communication station. It's actually located on campus. There are two big antennas, a 4-meter dish and then a 5-meter Yagi that you see there that are on top of the roof of one of the buildings next to the building where astronautics is. And then you can also see that there's a control room that we've set up. We actually use this every year. We teach, one of Dan talked about, one of the graduate courses we have is a hands-on course where you actually, the students get to learn how software-defined radios work, how to program things, how to look at a spectrum analyzer to understand what a signal is. And then the project course is a lost in space exercise where they literally have to sit and track satellites on the antenna and validate that they think they found it. So we have that available, and we can do research with that as well. As I indicated before, one of the coolest things that's happening in the industry, I think at least, we all have our pet projects, is this concept of servicing that's happening. The fact that we can actually go up and modify things after the fact. Dan said, for many years, you just throw the bloody thing up there and boy, you really hope it works. But now we have the chance to think differently because we can go up and actually service it. So at USC, we were lucky enough at the CERC to be part of a consortium that was developed to actually look at standards of how to identify rendezvous and proximity operations metrics that are available and proliferated worldwide. Because it turns out, believe it or not, that there is no such thing as a standard. The gold standard, if you will, honestly, has been NASA and all the work that they've done. But there are many companies that want to get into it, and you'd like it to be safe. So we were a part of that. And then the other thing that we have is we have a small test bed that's out there at the CERC, where we can have little floating devices so we can simulate frictionless environments relative to how spacecraft maneuver toward each other and work together. So let's see, I think any other, some other ones I can sort of show, but the other one that I'll talk about is we are working on this crazy thing that we started years ago, just because, honestly, it was just too cool. And it was something the students could actually work on. And this is what Dan and Garrett were talking about. Astronautics is all about systems and collaboration and working together. So we created this thing called a lunar lander prototype vehicle that uses an RC, a radio-controlled jet turbine engine in the middle of it to take out gravity. And it uses space-qualified paintball tanks. Yeah, there's supposed to be laughter there somewhere, but okay. Paintball tanks for attitude control. So
I thought it was fun.
Awesome, good. I appreciate it. So that's, yeah, no worries. So anyway, we have that. We actually build these out at the CERC. So I mean, you can sort of see that there's a large body of kinds of research that we've done. Oh, yeah, the other one I forgot to tell you guys about is this crazy, in terms of robotics, the idea that if you really want to go up and interact with things on space, right now it's a very structured environment where you have a single point on the spacecraft you'd like to attach. But we pitched this crazy idea to DARPA, and they thought it was crazy enough they accepted it, to create an octopus-inspired robotic arm that uses electroadhesion to go up and grab anything. So again, we were lucky enough to use the test bed we have to actually demonstrate things like that. So I only wanted to give you sort of a broad brush of this. You can go to the website and take a look at some of the other details and things that we're having. And yeah, so
that's phenomenal. Thank you so much for sharing that. Lots of great visuals to go with it too. Anything else related to research? That was definitely a lot.
I'll talk a little bit. I've had a kind of a career where I've changed directions a bunch of times. I started out in electrical engineering, and then early in my career I did hypersonic flight, and then a number of years on the space side doing electric propulsion, that is rockets that operate on electrical principles, that only on spacecraft, not for launch from Earth. In the last few years, though, I've switched directions completely, and now I'm working on autonomous vehicles. And actually, it isn't, the specifics are not space related at all. They're actually quadcopters and radio controlled cars. But the general principles are about autonomous swarm behavior, and about how it is that you can trust vehicles and other robotic objects that think for themselves. And it's partly simulation and partly experiments. And one of the things that's really that I personally enjoy about it is that when you build small autonomous vehicles in the lab, they have all these little computers and little gizmos in them, and you have 3D printers, and it's just everything changes all the time, and you can get all kinds of stuff done for very little money, because the whole makerspace world has sprung up in the last decade. So it's just a ton of fun to work in the lab now compared to 20 or 30 years ago, when most of what you wanted to do required specialized stuff that oftentimes cost $10,000 to $100,000.
Very cool. Very cool. Anything else? Okay. So I want to give a few minute warning here to our audience and have them start thinking about their questions. I want to open it up to the audience questions in just a minute, but some of you did this in your intro, but I'm curious if we could get kind of a quick run through of your educational background. I think this helps students as they're coming out of high school. They're looking at fantastic universities and engineering schools across the country that they've been admitted to. And I think it might be helpful to know where you all went to school and how you found yourself at USC. Garrett, do you want to get started with us?
Sure. Right. I started out in Lake Hiawatha Elementary
What about kindergarten?
School.
I need to know the kindergarten. We're starting with kindergarten.
Probably going back a little too far.
Lake Hiawatha.
Yeah. That's where I did kindergarten. Yeah. So yeah, I did my undergraduate work at University of Pennsylvania. I was actually a dual major there because I wasn't sure what I wanted to be when I grew up. So I was taking classes in business at the Wharton School, and I was also taking I was also a mechanical engineering student as well. So I graduated with two degrees, and rapidly found that I gravitated much more towards the technical side, much more towards my engineering studies than the business studies. I found that much more interesting, and decided I wanted to take a deep dive into engineering. So I went off to Caltech, and that's when I came out here to California for the first time, and ended up doing my PhD research there in multi-phase fluid mechanics. So, which is a fancy way of saying bubbles. So if you have questions about bubbles, I still might remember some of that stuff.
Awesome.
Probably help you out.
Professor Barnhart.
Yeah, so I went to undergraduate in Boston, high school in Georgia, and then moving to Boston, I had that accent, but then it evened out between the Southern accent and the Boston accent. So now
Quite a combo.
I don't have any accent. But that was undergraduate in aerospace engineering, and then I did a master's of engineering in aerospace and ocean out of Virginia Polytechnic Institute in Blacksburg, Virginia. I do not have a PhD. I'm very cautious about that because those that do, I have great deference and reference for. I am a professor in the department basically from the experience. So right after the master's degree in engineering, I went right to work with the Air Force Research Lab and did research for probably 13 years on all kinds of wild and crazy things within the Air Force. And then eventually helped start now it's 3 companies. One of them was great fun for a long time, traveling around the world until they stopped paying me, which is sort of a negative. The second one is Millennium Space Systems, which is actually still in existence here in Los Angeles, doing very well. And the third is a separate one that who knows whether it'll go or whether it won't.
I drive by Millennium. Well, back in the day when we drove to work, I drove by Millennium Space Systems every day.
Yep.
All right.
Yep.
Dan?
Well, I grew up in Seattle, and I've actually only gone to a very small number of schools because we didn't move around much. So I had one school for elementary, and then my high school was 7th through 12th, and it was actually the same high school Bill Gates went to. In fact, I was a freshman and he was a senior, so I kind of knew him. And he drove an orange Mustang at that time. I went to Caltech as an undergraduate, and I kind of jumped majors a little bit at that time because I wasn't sure whether I wanted to be an electrical engineer or a physicist, because what I was really interested in was lasers, and so I ended up majoring in applied physics, which at USC is what they call electrical engineering electrophysics. So it's really about the physics of devices and about the interaction of light with matter and how lasers work. And then while I was an undergraduate, I worked at Lockheed doing computer graphics. And back then we did actual computer programming in a language called Fortran. And this was at a time when graphics was not done in the movies yet or by TV commercial people. It was really only done by the aircraft industry. And in fact, it hadn't been that many years since aircraft moved from being drawn on paper to being completely modeled mathematically. The Boeing 707 was drawn on paper. So if you wanted to learn something about the design, you took a big calipers and measured on the paper. But the 727, if you wanted to know something, you asked a mathematical model. And aircraft and many other things have been that way ever since. But 3D graphics was developed by the aircraft companies and was pretty far advanced, really before the electronics companies or movies or anybody else got a hold of it. So I worked on that as an undergraduate, and then and then took a year off, and I was there for a couple of years. And then I went back to graduate school at USC in electrical engineering, because that's where they did lasers. And I kind of switched over to gas dynamics, plasmas, and then it turns out that in the aerospace engineering department, they were doing hypersonic flight, and a lot of the physics of plasmas and of hypersonic flight turned out to overlap heavily, and the stuff that I did with lasers turned out to be useful. So I ended up in the aerospace engineering department, and I didn't know anything really about moving flows at that time or about space. That all came later. One day I was teaching a course in laser interactions with gases, and a guy came up afterwards, a guy who worked at JPL, and he said, "Do you think you could use these in the plume of an arc jet?" And I said, "What's an arc jet?" And he told me it was kind of an electric rocket. And within a year, we had a proposal. We were working out at JPL, and I had my lasers out in his lab at JPL, and that kind of led into a whole research thing for many years at USC. And then it was, again, just in the last few years that I've switched over to doing systems engineering and autonomous
That's
vehicles.
fantastic. No.
Again,
And now all I want to
but
do
there
is
you have
ask
it.
questions about Bill Gates, because I think that I want to learn more. So I'm going to open it up to our audience and see what questions they have. So feel free to type your questions into that chat. I will watch them and try to. Sometimes people ask similar questions, which is fine. And we'll summarize them and kind of moderate as best we possibly can. Okay, so one of these questions, the first one from Brendan, thank you. This is a question we're getting in almost all of our admitted student sessions, which is what's going to happen in the fall and with the uncertain times that we're in right now. And this is all relative to advising, and I'm going to handle this one, but feel free to jump in if you have any other feedback. Right now, USC is considering that everything's going to happen as normal for the fall. Of course, that's the plan. Things can change, and will change as necessary, but there is no formal announcement as the fall as of right now. The staff and faculty done the most work here as far as pivoting all of their classes to a robust remote learning environment, and they're all handling their classes just fine. If we need to do that again, I'm sure that we will, but that doesn't necessarily change the classes that you'll take in the fall. You need to be on track to graduate, and the advisement sessions that you'll go through at orientation will be appropriate. The summer orientation programs that you'll go through in June will have all transitioned to online programs, and we'll have those registrations. If they're not available now, they will be available shortly. So if you decide to attend USC, you'll first go through summer orientation, where they'll do remote advisement. You'll register for your fall sets of classes, and if we change anything, we'll let you know, but that's the plan right now. Can we talk about you all, as far as what do you see from your students and where they go after their undergraduate years, going off to industry or grad school? I have some school-wide stats, but just for your anecdotal information of students you know.
Oh, well, I'll take that one because I've been watching our students graduate for many years, and the majority of them go to industry. They don't necessarily go to industry right away. A lot of them get their master's degree first, because one of the things about engineering is that a master's degree is an important degree in engineering. It carries weight in industry, and it's considered an important thing by itself, which is different than, say, science and mathematics, where a master's is something that you get really on your way to a PhD, or even not at all. But a master's is an important thing. And we have two ways of doing that. We have some of our students, quite a few actually, go off with their bachelor's and work in industry for a few years, and then their companies will offer them the opportunity to come back and get their master's, and they actually will pay for it. Some students decide that they would prefer to do it kind of all in one, and we have a program for that, which you may have heard of, PDP, the Progressive Degree Program, where students really get their bachelor's and master's all at the same time. Now, so by grad school, if you mean master's, I'd say probably 60, 70% of our students get their master's either right away or within a few years. PhD, it's a smaller number. It's maybe 10%. And our students have done PhDs at MIT, University of Michigan, are a couple. One went to Caltech. Actually, he switched. He's in theoretical physics and is pretty well known now. University of Washington. We've had quite a few students go on to PhDs, but it's a small fraction overall. It's
and then from
10%.
our surveys of graduate, and I think what's important to outline there is what Dr. Erwin mentioned, is that this isn't a mutually exclusive decision. There's no such thing as careers versus grad school. In a lot of situations, it's a combination of that as students go on. when students are coming out of our undergraduate program based on our commencement surveys, we see it's roughly a little over 70% of each graduating class are going straight into industry. That doesn't necessarily mean that they're not going to be pursuing a grad degree at the same time. A lot of those companies, Boeing is one of my favorites, tends to pay for the grad degree. And sometimes that's part of PDP, sometimes part of a distance education project, or something that they'll do later on down the line. But I think what's important to understand is that industry jobs are available with your bachelor's degree. It is not a degree that you necessarily need a master's degree to get a job. Of course, master's degrees are going to be important with the further education, the further advancement of your education, but the bachelor's degrees is sufficient, and students are doing quite well and successful right after undergrad. Okay, so Jared asked this question. I'm just going to go for it. I'm really interested in space travel and aerial transportation in general. What you all think would be the best course of study to follow? Aero, astro, or mechanical? So it's a fight. What's the best? Aero, astro, mechanical, and we have somewhat of a biased audience, biased group here. So let's see what happens.
Astro, of course.
Clear winner.
Well, okay. I think if your interests are kind of broad, well, the broadest of the three majors is mechanical, and you can't go wrong with mechanical. Every industry employs mechanical engineers. The other extreme is the most focused degree of all three is astronautics. And if you pick astronautics, it says right on your transcript, right in your diploma, that your goal is to be in the space industry. Now, that doesn't mean that's what you're required to do. In fact, believe it or not, some of our graduates have gone on, actually I think only one of our graduates, but I won't exaggerate, has gone on to medical school, and another of our graduates has gone on to a PhD in biomedical engineering. So I wouldn't say it's the case that an astro degree pigeonholes you so you can't do anything else. But certainly if you take astronautics as a major, it will best position you to work in the space industry and space related research fields, because frankly that's what it's about. And no other major hits these space related issues as hard as astro does. So if space is what you want and you're for sure about it, then astro is what you want. If you want to be broader, you can do aerospace and do air vehicles and space vehicles, rockets, and you can take courses in astro, you can take courses in aero, and so you can be as broad as you want. But you can switch back and forth. Even if you stay in astro, you can do really a lot of things. So I wouldn't worry actually about the decision that much.
Garrett, do you want to go ahead? Sorry.
I think that final bit of advice there, that conclusion that Dan just made is really important, which is this choice is not irreversible. If you decide one or the other, you're not committing yourself for the whole rest of your career to doing that particular area. So yeah, I think that advice is excellent, which is don't worry about it. just pick something that feels right now and see how it goes.
Actually, I'll say one kind of general thing about companies and employers in general. They don't care necessarily so much about what it says on your transcript. They're going to ask you what you did and what you know. So what you do while you're in school, what projects you took part in. Did you do Rocket Lab? Did you participate in research? Do you have any are you co-author on any research papers? They're going to ask you about what you have done and what you can show them, probably at least as much as
absolutely.
what you
And I think that's the issue. You know, it's a young engineer's mind, right? That there's some sort of right answer to this problem of what do I need to do with my undergraduate degree, and your undergraduate degree doesn't necessarily dictate your future. So that's the first thing I would tell everybody. And just that's why I liked going through your academic backgrounds. All of you had very unique and individual academic backgrounds. None of you have the same. And what people do, like for example, Garrett, you might want to talk about this idea of, let's say your goal is I want to work at SpaceX. Well, SpaceX is hiring aero, astro, mechanical, electrical, computer science, and a bunch of non-engineers as well, because it takes a lot of different people to kind of get that business going. So there isn't one specific path to work at SpaceX, for example, right?
Not at all. And really, like you said, we don't really care what the title is on the diploma. We just whether it's electrical, We just want to know what you're good at doing, and what you're and really just your capabilities as an engineer. And we always feel like a good engineer could move from one topic to another, as long as you have a basic grounding in the fundamentals and a really good cognitive ability. At SpaceX, we're comfortable putting you anywhere that you're interested in, and where you're passionate about, and where you're going to do your best work. So none of this really pigeonholes you or confines you.
We had a question about research opportunities for undergraduates and how undergraduates get involved. And then more specifically, are there research opportunities on campus? I think that the fantastic detail that we got from Professor Barnhart on ISI made it sound like all the research is off campus. But can we talk that, well, also it's not incredibly far, but can we talk about how undergraduates can get involved in research on campus, and what you all see as undergraduates' place in research opportunities?
I'll start with that one. It's very easy for undergraduates to get involved in research, and pretty much every faculty member is doing research at some level, and pretty much every research active faculty member has projects where they need help, either stuff they're working on right today, or things they'd like to work on, but they don't have enough people to help them with it. And I have right now one undergraduate working with us, along with in our group, along with several PhD students. Many faculty members have a lot more. Some have 6 or 8. Dave, you have quite a few that commute from USC to ISI and work with you. The thing about one thing that scares people away, but it really shouldn't, is you think, okay, I don't know anything about research, but that really is not something to be worried about at all. All you really need is the interest to learn about something and find out what the issues are. And you think of research as some magic thing. It's not. It's just people trying to move forward, and there's problems all over the place. Some are software related, some are experimental related, some are electronics related, some are purely mechanical. We need something to, I don't know, something to bridge from here to there, and you need to design it. There's really all kinds of ways you can plug into research. And the more you get involved, well, I'll tell you what very often happens with undergraduates is they'll take on some piece of the project that the PhD students maybe haven't gotten to or don't quite know how to do. And within a year or sometimes longer, the undergraduate will be the expert in that area, and the PhD students will have to come to them to ask about it. And it also often happens that undergraduates are important enough in the research that they become, as I mentioned, co-authors on papers. And that is a thing that's as good as gold if you want to go to graduate school, because graduate school, you have to get in with recommendation letters, and they're not the like 3-line letters that some professor will give you if you got an A in their class. These are more like the 1 to 1.5 page letters that say that this undergraduate worked in my lab for 2 years, and these are the projects that he or she worked on. We had a lot of discussions. I thought she was wrong about this, but she turned out to be right. Things like that. Those letters get you into graduate school. And more generally, research is a ton of fun, and you learn all kinds of things that you didn't know you knew how to do. Because in research, you have to figure things out. I mean, you need to, a lot of times, nobody knows how to do something. So you just have to go find some new approach. And maybe it means figuring out from scratch. Maybe it means somebody in some completely other field knows how to do this. So you have to be agile and open in research. But that's true of engineering too. Because a lot of times, something that you need to do, somebody else knows how to do if you can just figure out who.
Yeah, so I mean, to dovetail on that from Dan, really, the research encompasses sort of 2 things. One is hands-on knowledge of pieces of equipment or hardware that you can put together to create a prototype or an experiment. And then the second is sort of the innovation and the exploration of an experiment to sort of come up with something new. So the cool thing is that honestly, there's a number of opportunities that I'd like to think is unique in the Astronautical Engineering Department in particular, that from freshmen all the way up to PhDs can get their hands on hardware and in some way, shape, or form drive or create new research. The biggest ones on campus for the freshmen that come in, no question about it, is the Rocket Propulsion Laboratory and the Liquid Propulsion Laboratory. Both of those are very hands-on, no questions about it. Some do more research, exploration, some do more applications associated. But both of them are there on campus and actually encourage students to participate. The activity that I have out at the Space Engineering Research Center, yes, it's not on campus per se. There is a shuttle that goes there every hour, every day in normal work week. In general, from a freshman standpoint, research, sometimes you have to dovetail in. You take a lot of courses, and so you may not have as much time during the day, let's say, as a graduate student does. Graduate students typically have classes in the evenings just by nature of how the classes are put together. And so out at the CERC, I have in general during the day a lot more graduate students who take that opportunity. But that's notwithstanding, I have a number of freshmen that are actually able to come out. The other thing is that, as Dan said, there's a number of professors on campus that are doing things in particular. The other thing we've done, which is unique in the astronautics department, well, I mean, I think all the other departments have it, but we have course numbers called ASTE 291 and 491. And they are focused particularly on discipline areas for hands-on activities. There's one for rockets, one for this lunar lander vehicles, and one for microsatellites. So this past year, we were lucky enough to start up a 291, 491 course series. You take 291 first semester, then you take 491. That was building a spacecraft. And it was one of the first times we were able to do that. So, and a lot of that work is done on campus, even though in the end, the clean room to put it together in might be associated at Marine Array, but then we work that out in terms of students to be able to get there to get their hands on. So there are opportunities.
That's fantastic. I think we got time for just maybe one or two more questions. One is from Henry Adam. Dean, you were supposed to said this, and then I, as a result, echo it a lot, which is that the goal of the engineering school is to engineer a better world for all humanity. How do you see the expansion of the space industry helping to better the world?
Wow, that's a pretty philosophical question, but I'll take a shot at it. I think, the space industry has revolutionized how we all live our lives, and probably the biggest impact on a daily basis is the telecom industry, with the reliance on space assets to provide television and other broadband communications. That's only going to grow as it looks like, if these new efforts are successful, might be moving to space-based internet and connections instead of land-based or cellular connections. So I think that that from a communication standpoint, it's really affected us. It's space assets also from a navigation standpoint. I mean, nobody could get anywhere these days without looking at their phones and looking at and using GPS to find their way from point A to point B. I think if people had to use maps again or something, we'd all be lost. So there's those aspects of how the space industry has really changed how we live our daily lives. But looking at it from the part of the space industry that I'm very passionate about, which is human space flight, our ability to travel off this planet and expand the human presence, and hopefully one day to actually establish permanent human presence in other places in the solar system. If you take the really big picture look and a really philosophical look at this, it's all about survival of the species. Right now we have all of our eggs in one basket on this planet Earth, which is by far and away the best place we know of in the entire universe for human life. It's where we evolved, and so we're particularly well suited for this place. But it's still, it's like having all your data on one hard drive without having a backup. And the idea is that if we could move out to other places in the solar system, that's kind of our destiny as human beings. We like to explore, we like to move on to new worlds, and I think if you take the incredibly big picture view, it's about that.
I can say something too as it relates to science and our understanding of the Earth, because the GPS hasn't just provided navigational information. What we've learned from GPS has made knowledge of the Earth's gravitational field incredibly accurate, which in turn means that spacecraft in orbit are incredibly precisely located, which in turn means that a spacecraft looking down at the Earth and making measurements can make very accurate measurements. So there's a lot of what we know about the evolution of the Earth, the ice caps, continental drift, and more kind of physics-based measurements of the atmosphere and things related to the development of climate that you can only do from space. And more generally, our understanding of the Earth's place in the solar system and the way the solar system operates. All these, there's much of that we can only learn in space. And nobody's told me jokes so far, so I'll mention one. At some point, somebody asked a soldier what he thought of the military's reliance on space, and he said, "We don't need any space stuff. That's not important at all. All I need is my rifle and my GPS, and I'm good."
That was phenomenal, and I think a really great place to wrap it up. There are a number of questions here about the kind of the curriculum in general, about Engineering Plus and PDP and things like that, which I definitely handle in our Viterbi keynotes. And so if you're in the audience, you haven't attended the Viterbi School keynote sessions that run on Tuesdays, we have another one coming up this Tuesday at 9 a.m. Check your admission portal for those, where we talk a little more broadly about these programs. We can get into detail on that. This was specifically about the discipline of astronautical engineering in our faculty discussion. I think that there's a question that said, what makes AeroAstro stand apart from other STEAM universities programs? I think the answer is everything we just talked about for this last hour. I mean, these faculty members are just a small sample of what are at our campus, and the drive and the compassion, the overall level of just passion in general towards the discipline and working with students. This was not pulling any teeth to get these guys on here. And so I'm really appreciative of your time. Thank you so much. I hope you all and your families stay safe. And for everyone that's watching, thank you so much for joining us. We look forward to hearing your decision about whether you'll join us at USC by May 1st, which is the National Candidates Reply deadline. Please remember to submit that deposit no later than May 1st. That's at admission.usc.edu/status. If you got any other questions for us, you can find us at viterbiadmission.usc.edu, or give us a call at 213-600-9919. We're answering those phone calls on our mobile devices at our home. So anyways, thank you so much, Professor Barnhart, Professor Erwin, Professor Reisman. Thank you so much for joining us. Thank you so much. I would love to keep you on, but when I close this, it's all going to kill you. So we're going to take you out of here. So thank you so much, and fight on, everybody.
Thanks, guys.
Cheers. Thanks very much. Pleasure to see everybody.
Good luck, everyone.